Hello everybody, I'm Yuanqinq Wang. I'm an independent fellow at New York University. I'm also a Schmidt Science Fellow. And I believe, sorry for the slightly obnoxious title, I believe I've enumerated all of the adjectives there are that could describe both force fields and cocktails. Because I name all of my packages as cocktails. So by briskness, smoothness, and intricacy, I just mean speed, stability, numerical stability, and resolution or accuracy. So force field is a model that would map from the geometry of a system to a scalar that we call energy. Of course, the true force field that everybody wants to get access to is almost always intractable. So as computational physicists, people come up with this kind of surrogate models denoted by U hat that would somehow approximate the true energy of any systems. And of course, if you have a more accurate U hat, you can derive this by whatever divergence you might use. You will find that your density estimate, your probability density estimate of your physical state of the system is going to be a lot closer to the true physical probability density you want to measure. So in this talk, and I believe this is sort of like a common notion adopted by the field, that we say force field is a parametrized mapping from geometry to energy. It doesn't have to be parametrized, but it usually is. So computational biophysicists or computational chemists, they're good at simulate a system either very quickly or very accurately, but never both. So we can never get access to that lollipop on the design space, which is the perfect balance between speed and accuracy. So in this talk, I'm going to talk about two efforts that I've made during the last 3 to 4 years while I was still doing my PhD, which is to make MM faster and make machine learning potentials slightly, make MM more accurate and make machine learning potentials more faster. So I guess these are two things that Anger's theory would hate. One is MM and the other is scalarization-based machine learning potential. But I think these two have a little bit of utility because they are so much faster than the sophisticated models. So in case anybody in this room don't already know this much better than I do, here's a very brief introduction of the MM force field. MM force fields tend to abstract all the atoms in your physical system as this kind of charge-carrying particles, and they interact with via these non-bonded and bonded interactions, where all of the bonded terms are just I'm sorry, there's a typo here, but all of the bonded terms are just a little a spring, and all of the angle are similarly a harmonic term, and all of the torsion terms, either proper or improper, are just a simple Fourier series. And of course, it's very ridiculous. Like we know that physical systems don't behave like this. We know that bonds are not springs. If you stretch them far enough, they will break instead of going to infinity energy. So I firmly believe that these kind of systems, these kind of methods will just die within a few years. In 5 to 10 years, nobody will ever be doing MM simulations anymore. But people are doing that right now because we do not have a better alternative, because our hardware cannot afford us to run very long time step of simulations. So as a measure of almost hospice care, we want to press the last bit of juice out of these functional forms. So let's talk about another thing that's horrible about MM, apart from the functional forms, which is the atom typing scheme. So what are the atom typing schemes? So you realize that we abstract all of the bonds, angles, and springs as these kind of ridiculous objects. And these objects, they need parameters, right? So your bond would need a bond constant, a force constant, and a equilibrium value, meaning that where the spring want to be and how hard it would resist it when you push it or squeeze it. So people traditionally do this via what's called atom typing schemes. So if you go into OpenMM, this is actually a bit of code that's pulled from OpenMM, you'll see that all of these force constant and equilibrium values are programmed as such. So if you look at the first line here, it says that if you have a bond and the first atom is a water oxygen and the second atom is a water hydrogen, then you had a hydrogen oxygen bond in the water. Then it should have length, which is equilibrium value, so and so, and force constant, so and so. And the same thing goes for angles. So it's a giant lookup table. And the first bit of the table, which is the type 1, type 2, type 3 thingies, are called atom types, and they're extracted from an actual table that's written down on a piece of paper, which is kind of hard to imagine in 21st century, but people do this anyway. So this is the atom type table published in the very popular and classical GAF, or generalized amber force field, paper. So it says that, okay, if I'm a carbon, if I'm an sp2 carbon and I'm connected to oxygen and sulfur via double bonds, then I am questioned as atom type C or atom type number 1. So this has a few problems. If you look at if you look at the molecule on the left and the molecule on the right, you'll see that, okay, this is a sp2 carbon, this is aromatic, and it doesn't have any other fancy atoms connected to it. So the atom type on the left is going to be a Ca type, and the atom on the right is going to be a Ca type, meaning that they're going to be the same type, and they're going to share all of the parameters. And this is something that would make a chemist murderers, because they behave drastically differently. If you consider the CH bond, the one on the left is going to be very strong or weak. I forgot organic chemistry for a long time. I think it's going to be stronger, right? Anyway, the strength is going to be different. That's the whole point. But they are going to have the same parameter. And of course, optimizing the parameters for all of these values, all of these k's and the length, etc., is going to be very easy. You just do a gradient descent type of thing. But the difficult thing is going to be to optimize the atom types at the same time. So your optimization is going to be bounded by the resolution of the atom type. As long as you keep these atom types, there's a threshold up to which you can optimize. You cannot go beyond that. But let's take another look at these tables. So what are being considered in this table? There are actually 3 things that are being considered if you group them together. The things that are underlined in red are node attributes. Underlined in green are number of neighbors, whereas the attributes not underlined in blue are neighbor attributes. So in graph modeling language, people tend to use neighborhood multiset, which is the multiset just means the number and the collection of number and nature. They use the term neighborhood multiset to denote the number of neighbors as well as the neighbor attributes, right? So basically, the force field typing table is a function that would map from the joint space of node attribute or node attribute and neighborhood multiset to some representation. So in this case, the representation here is a class, is a type, is a category. It's a horrible representation, but it's a representation nonetheless. So if you want to optimize this function, if you want to optimize this map, then you might want to consider to have an optimizable function from the node attribute and neighborhood multiset, which is keeping the same signature, to some sort of a node representation. And you might write it down this way. So if you call your node attribute HV and your neighborhood NV, and you can put a little aggregation function on top, you will realize that this is exactly the master equation of graph neural networks. So we say that roughly the force field atom typing tables, they have the same signature as a GNN. And we hypothesize that GNNs are at least as expressive as legacy atom typing schemes. And it's very hard to quantitatively or theoretically characterize this hypothesis, because it's very hard to theoretically characterize the expressive power of legacy force fields, right? It considers so many things. And we do this experimentally. So what we did here as an illustrative experiment is that we took a bunch of molecules from the zinc dataset, and we used some chemoinformatic toolkits to assign the basic traditional atom types, and we use a vanilla graph neural network to try to fit these types. And we see that on a test set, on a Hao-Dao test set, we achieve over 99% accuracy in recovering these atom types. And places where we make mistakes are places where human experts are likely to make mistakes as well. So for example, this kind of CC to CA confusion is an aromatic carbon and aromatic carbon infused ring, which is a parent class and a child class. So based on this hypothesis, we develop a framework called extensible surrogate potential optimized by message passing, or SPLOMA. So the idea is that we would take the output, the representations come up by GNNs, and we would combine them to form representations for bond angles and torsions. And from there, we just need a simple linear or nonlinear projection to get all of the parameters that you might need for a force field. So this entire pipeline is conditioned on a collection of neural network parameters called PFF, and the output of this neural network is a collection of force field parameters. PN to PFF, the collection of force field parameters. And of course, this is end-to-end differentiable, as is all the neural networks. And as a result, the energy is differentiable with regard to all of the PFF parameters, as well as all of the PNN parameters. So what you can use this framework for is that you can use a machine learning generated force field parameters to generate some properties, namely energies and forces, and you can fit these properties to some experimental data or some quantum mechanics data if you treat that as your reference. It is worth noting that so all of the colorful lines here, they are parameterized by a neural network, whereas all of the black lines here are just simple transformation. So all of the neural bits in the inference time only needs to be executed exactly once for each system, whereas the black arrows are as fast as your traditional MM. So when you have a system and you use SPLOMA to parameterize it, you will just run this GNN once. It doesn't matter how slow it is because you only need it once. And the energy evaluation step is going to be as fast as like Amber or GAF or OpenFF. Okay, so we briefly talked about how we're going to go from an abstracted chemical graph to the atom embeddings or atom representations. Now we're going to also touch upon how do we combine these representations to form bond angle and torsion representations. So the only thing that we need to take care of is that there is a little bit of symmetry in the molecular graph in the MM sense, which is just the mirror symmetry. So if you index your molecule differently, it should not change the parameters or the representations of your bonds, angles, and torsions. For example, if you have a torsion that's 0, 1, 2, 3, if you name it 3, 2, 1, 0, it should give you the same thing. So the dumbest way, but the most efficient way, as it turned out, to handle these kind of symmetries is to go through a scheme called Januzzi pooling. Meaning that if you have a non-permutation invariant function and you want to get a permutation invariant function, what you can do is that you can enumerate all of the permutations and average them. So this is what we did here. To come up with a symmetry preserving representation of the torsion, we can just enumerate 0, 1, 2, 3, concatenate them, go through a non-permutation invariant neural network, and do the other way around and add up or average the result. So here completes the entire end-to-end pipeline. And before we dive into QM data, we generated a bunch of MM tasks just so we have a good idea of whether this pipeline is actually useful, whether it's actually learning anything. So we generate a bunch of MM data using GAF force field, and we try to use our SPLOMA framework to fit the MM data. And it seems that we can fit the energies almost perfectly, and we can also recover the underlying parameters that's dictating the energy landscape. So I think that's a bit of a proof of concept, ensuring us that we are finding the maximum likelihood fit, or something in the vicinity of MLE fit of MM potential. Now we have reasons to suspect that we might be able to find likewise MLE fit if we have actual QM data. So we generated a bunch of QM data sets that's very close to the minima, so that it can be handled by MM, and we fit our Espeloma pipeline on that, and we see that we can outperform all of the traditional legacy force fields. Well, it's worth mentioning that, so one of the datasets that we use is this OpenFF Gen 2 optimization dataset. It's a drug-like data set that's generated by OpenFF people, and they also use this dataset to generate their OpenFF 1.2.0 dataset, but we see that we are doing a little bit better than OpenFF on this specific case, meaning that it suggests that it's perhaps a superiority in the fitting scheme rather than the data. And then we also look at this kind of heterocyclic ring dataset, which is very exotic, and you can see that all the legacy force field here, they kind of fail horribly. Why is that? If you look at one of the typical cases here, you'll see that, for example, that the molecule here, you might think it's aromatic, but if you calculate the Hugo rules, it's actually not aromatic. Whereas the chemoinformatics toolkits, because they have very limited resolution, they thought it's an aromatic molecule. So when you initialize them with a flat geometry, you'd want to stay there, and if you optimize that under QM, it will become pyramidal with the nitrogens, and the energy will go up. Whereas actually the QM energy will go down when you optimize from the flat to pyramidal shape, because they're not actually aromatic. Espeloma can capture this behavior because it's trained down so many molecules in the training set that look similar like this. And finally, we also train on PepConf datasets, which is just a bunch of peptides, and we did slightly better than Ember. So this, I believe, is the very first simulation of resulting from a force field that's self-consistent on a protein and a small molecule ligand. So we can use the same force field Espeloma to parameterize both regions of the system, and it would allow you to do something that you can never ever do before. For example, this parametrization of a covalent adduct, and we can even use this to run some binding for energy calculations. And in the second generation of Espeloma force field, which will be published tomorrow, actually, we see that we can achieve very good RMSE in terms of not only just the energy, but also the binding free energy compared to the experimental data. We can do a lot better than Ember force field and open force field, small molecule force fields when we predict the binding free energy. And since this is a SciPy conference, here is some code. You can conda install Espeloma, and you can throw in your favorite system, and in 3 lines you can parameterize the entire system and give you an OpenMM object you can use to simulate. I'm going to skip a little bit because I'm running out of time, I believe. So yeah, that concludes the first part of the talk, which is Espeloma, which is the model to make MM a little bit more accurate. And another work that I've been doing for quite some time is thinking about how we can make state-of-the-art machine learning potentials slightly faster. So there is a line of research showing that although the tensor product-based or spherical harmonic-based equivariant graph neural networks are very powerful, very expressive, and very data efficient, all of its representations can be approximated by lower-order tensors. So lower-order tensors, or even the scalarization of just level 1 tensors, order 1 tensors, can already approximate whatever whatever function that can be in a universal manner. So we predict, we're proposing our spatial attention kinetic network paper, which is acronymed as SciK. We propose this very simple functional form where we take a neurally parameterized linear combination of edge vectors as the descriptor, and we see that we can predict the energies and the forces on some popular benchmark datasets pretty well. So it's not quite as good as an equip, but it's about 50 times faster. And because we have equivariant output, we can directly output or predict the time evolution of some dynamic system. For example, on the left, we predict the simulation outcome of a charged particle. So we have the initial pulse, we have the initial velocity, and we can predict where the particles would be at a given timestamp. And of course, we don't have to limit ourselves to a microscopic system. If you have a guy walking and you give me his position and velocity at a given time, I can tell you 5 or 10 seconds later where he's going to be. All right, so yeah, so I guess for the remaining of the time, I would just like to talk a little bit about the lessons sort of learned during these exercises. Like I said, I think in 5 or 10 years, nobody would be running MM anymore. Maybe that estimate is a little bit too aggressive. But I think as we have more hardware power, we're going to shift more towards these kind of more flexible terms, because there are papers after papers showing us that there is so little correlation between MM force field and quantum mechanics calculations, which we take as our reference or a gold standard. But on the other hand, machine learning force fields are also very hard to domesticate. They behave wildly. They could be unstable, and it's very hard to achieve the balance between the stability, accuracy, and the speed. So where should we go as our next step when we design our new generation of force fields? There are a few things to consider here. So for example, an Espeloma model or any kind of MM-based model, we hard-code its topology. So we hard-code the bond, they never break. We hard-code the angle, they never break. But sometimes they do break, but we don't want all the bond to break for most of the time, right? Whereas something like SciPy, they infer the topology. There's no notion of bonds, angles, and torsions. They're just a bunch of particles hanging around here. So would it be possible if we can inject a little bit more domain knowledge to tell the algorithm which bonds should we be breaking and which ones that should never ever break? And there's a paper that's coming out that came out a year ago saying that it's actually doable using some constraint. So during your message passing, you can just tell the system that this bond or this distance will stay within the threshold or as a constant value. And something like Espeloma would do message passing exactly once, and then everything else is just local. Whereas any machine learning potentials would need to do message passing on the fly, so they would do that over and over and over again as your geometry change. And that, of course, could be very slow. So is there a middle ground? So one paper from Kaczynski group, they talk about, can we have this kind of local models and come up with a reasonable representation, and we don't ever have to do message passing again during the simulation. And traditional MM models have some merit in that they are interpretable. So we can map everything into these cute little objects, bond angles, torsions, residues, chance, helices. None of them exist, right? But they're interpretable anyway. So we can imagine how they move. We can visualize them. And you have to admit that sometimes the functional forms are kind of elegant, because you can tell the system how they should behave. Whereas something like Sake or any machine learning potentials, they are very black boxy. So is there any middle ground? So can we use, for example, machine learning to parameterize some combinations of the interpretable terms, namely higher order class 2 force field terms, namely the higher order harmonics or polynomials, or these kind of Gaussian RBFs, for example. And in terms of the ecosystem, we are migrating all of our code base to JAX, and we're creating a new ecosystem where we can rapidly create, design, and test these kind of systems with a different balance between speed and accuracy. And by the way, I'm sorry, and one piece of advertisement. And many of these force field development are also playing a huge role in protein folding. So I'm involved in this consortium called OpenFold, where we pull the industry resources together and try to develop the next generation of protein folding model. If you're interested in that, either in contributing your work or in funding us, that's even better, please reach out to me. And with that, I would like to thank everybody for listening, and I would like to thank my previous colleagues, and especially Ken Takaba, who did most of the work for the new generation of Espeloma. And I thank all of these companies who are using our machine learning powered traditional to do some of their in-house screening. With that, I would like to take any questions you may have. Thank you very much.
Thank you so much, Yuanqinq. A great talk. I hope there will be a number of questions. Any questions?
So you spoke about some of the advantage or some of the better accuracy of Espeloma compared to, was it OpenFF 1.2, or have you done 2.0 as well?
So for the new generation, we've done GAF 2.11, Open Force Field 2.0.0, and Open Force Field 2.1.0.
Oh, cool. Okay.
Yeah.
What are some of the so it seems to give better accuracy. Are there any limitations of Espeloma compared to like the OpenFF like latest that you know of?
Yep. So you found a bunch of limitations, you and your colleagues, right? One of them is that we tend to have these kind of weird geometries, but we did fix most of them in this new release. For example, we currently we're doing both force matching as well as energy fitting. So it's not just the regression on the energies, because forces, they give us so much more information. And we repeated many of the open force field benchmarks, and this is one of them where we try to have a QM optima, and we use some LBFGS optimizer under different force field to optimize away from the optima and see how far we can go. And it seems that Espeloma, in not just this benchmark, but an array of benchmarks, can stick closer to quantum mechanical optima.
Okay, cool. Thank you.
Thanks.
Any further questions? Yeah, of course.
I am curious. You drew a direct comparison in that table at the end, comparing Espeloma to Saki about the different molecule representations. And how do you encode something like? Clearly, formal charge is all made up. And so here you're saying it's no longer a hard-coded topology, but it's an inferred topology. And in a case where you do have an atom or a molecule with a net charge, how does that information get to the inferred topology?
Well, you can just encode that in the input, right? You can just encode that in the input, and don't worry about that. You don't have to have an inferred object where you also interpret. What I mean by infer here is that, for example, bonds, you can infer that clearly. It could either be like a tension score, or it could be the distance that you can see during the course of your simulation. But in terms of charges, I'm not sure. For these machine learning potentials, what people usually do is that they just input that as one of their features.
Okay, so an atom that begins charge would basically be assumed to continue being charged through the whole simulation.
We can assume that the information about charge will not be completely lost during the simulation.
Cool, thank you.
Yep.
Further questions?
So thank you for a very interesting talk. So for the species embedding and the formal charges and such, do you stick with the list of chemical species from the GAF table, and have you tried playing with other ones now that you have a more flexible model?
So currently we stick to whatever GAF and open force field is using, because we have a limited training set. So for something that's like metal, we don't have the data to do that yet.
Yep.
Very cool talk, thanks.
Thank you.
And I'm just curious what kind of computing resources you need to construct some of these models.
Oh, right. So on a 1080 GPU, the newest version of model takes less than 24 hours. And this is a quite interesting thing, because the force fields that we're comparing with, some of them took like 40 years of development, namely GAF and Amber. But now you can just have a GPU, not even the best GPU, some GPU for 24 hours, and you have a new force field.
Last question. I think that I'm very happy about all the talks that we had in our session. I think about a great number of really interesting talks. Let's thank our speaker again.
Thank you.